Hello everyone, my name is Dimitri. This is going to be the summary of the Basiclib class we did, and my slides will try to summarize everything we've done, and it's going to follow the same structure as the presentation that is uploaded in Moodle. So if I might sound a bit confusing or make no sense, you can always refer to those slides, but hopefully like my little summary will summarize everything you will need to know. So the first thing to look at is the big numbers. So in C++, when we define a variable of type integer, by default it's going to be assigned 32-bit integer, which can store up to plus or minus 2 billion values. So for example, if we wanted to get time, and in C++ timers store seconds passed since 1970s, and if we convert the 2 billion seconds, it's gonna be 68 years. So in 2038, all our C++ programs, servers, and the timers that are associated with them will wrap around. It will result into minus 2 billion, which is a problem because that's pretty much gonna mess up everything. So to solve that problem, we have to use the 64-bit integers, which can store up to plus or minus 9 quintillion values. I don't know how many zeros are in there, but it's big. And when we convert that from seconds to years, it's going to be 292 million years. So that definitely solves our problem. So now just to show an example in C++, first of all of that is defined in Basiclib types.h. So for Linux, to have 64-bit integers, we have to type def long int, which is here for signed, and same for the unsigned. And for Windows 32, here we have underscore int 64 for the signed version, and for the unsigned, same thing, but you have just to add unsigned. Which, on the unsigned, will mean that 9 quintillion will be will go from 0 to double the 9 quintillion. So in the example, we have an integer which is just called big int, and the assigned integers can store up to 2,147,483,647. That's the maximum they can store, and once you add another 1 to it, it will wrap around and go into minus 2 billion, so 2 billion blah blah. And if you keep adding them, you'll see what's gonna happen when you're gonna print out. And then same was done for the 64-bit integer. I just took the 2 billion from here, pasted in here, and then I add 1, and you'll see that it's gonna just keep growing. And if I add another 2 billion to it, the number will keep growing as well. So it's just gonna prove the example that it works. So here we have the standard 32-bit integer, 2 billion something. Then we add 1, it wraps around, it becomes minus 2 billion with the 8 at the end. And if I add another value like 1000 something, it's gonna start to shrink. It's gonna become smaller. It's kind of a bit strange because when you add 1 here, it becomes minus 2 billion, and with the 8 at the end, when you increase more, it actually starts to decrease in the value. I don't know why, but that's the way it is. And for the 64-bit one, you can see it's still plus value when we add 1, and if we add another 2 billion, it still grows in size. So that's the little example. Then we're gonna move on to the next section. So next is time and frequency. So when we include windows.h file, there is a getTime function, which is a standard function of Windows, but it's not very accurate since it can miss dozens of milliseconds, which is no good for us. And there is an alternative approach for more accurate results. So what we have to do is call a couple of functions to get more accurate time. So in Windows there is a query performance frequency. This returns as a value that shows how frequently is the counter updated every second, and this value never changes because it all depends on our CPU. And another is query performance counter, which returns to us the number of ticks that has been passed since the system was started. And then what we have to do, like for example, to get the milliseconds, we take the frequency divided by 1000, and then we divide the ticks by that frequency, which will return the milliseconds at the end. So, but in Linux it's a bit easier. So you just go get time, like you just type in that function. So it's the reference to the time structure t, and 0 is the time zone, and what it returns is the microseconds. But it's a bit maybe too accurate what we need, so milliseconds will do just fine. Then to show the example, actually first we're gonna look at the Basiclib time.cpp. Here are all the includes we need for all those operations, and here we create our class Win32 performance counter, which will be used after that to get the milliseconds, like by just calling one simple function. But in this class we do the query performance frequency that was shown in the slides, and what we do, we have to typecast the 64-bit integer because this is the standard Windows function, so it can't take 64-bit values. Don't know why, but that's the way it is. So this is what we do, and these are all the calculations we have to do. And then like the get time milliseconds is the base function from which we can further take minutes and hours, days, and again we call that query performance counter, and then we divide that by the frequency that we have got, and then to get the seconds we just divide by 1000, then milliseconds 60,000, and so on. Now just to show the example, so here I define the signed 64-bit integers, for F for frequency and T for text. So we get the frequency, then we print it out, then we get the text and we print it out, and then we do that calculation to get the milliseconds. And as well I call the functions from Basiclib called get time milliseconds to show that this is the correct calculation. So when we run it, you see like my CPU has a frequency of like 2 million something, and I think my system has been running for like 2 days non-stop now, so it's been a lot of ticks since it started. And this is the milliseconds that we calculated from the t divided by frequency, and then just calling the basic lib function get time in milliseconds. And yeah, the results are the same, except like at the end is 8 because it took 4 milliseconds to print out these lines of code. So that's the example for the time and frequency. So I'm just gonna move on now. So continuing on, just to quickly talk about time and date stamps. This is just like an example of the code that I will type in C++, but I'm just gonna go into the C++ and explain some code. So in Basiclib time.cpp we have the timestamp function, and what it has, it's an array of characters, each size of 9, and then we have to get the time and convert the structure TM format. So we have this time value, and it has to be equal to time 0, which is going to be the local time, and we need to point it to a structure, and we call it B, and then it's equal local time, and we have to pass in the reference of the time, and then we have to print the time to the string, and what's going to take in is the array of characters. Then we have to say the size of the string, which is 9, and this is the format you have to type it in, and in order to get the like hours, minutes, and seconds, and B is just to pass in the structure is just the way it has to be done this way in order to get the timestamp. And for the date, it's exactly the same. All the changes, the size of the array of characters, and the what you have to type in up here, which is year, month, and days. There is also a timer class, which when you create the timer class, it starts with time 0 and initial time 0, and as well you can reset it, and whatever you pass in here will be the time which the timer will start at, and just to and as well then you can get the milliseconds and seconds from that class. So the example is like I have a time t, like everything like that was in that function. So when we print it out, it's gonna give us the hours, minutes, and seconds, and then I created a class type of type timer, and what I do, I reset it and set it to 30,000, which is like 30,000 milliseconds is 30 seconds. So when we run the program, you can see like when I run the program, like the local time is 9 o'clock, like 25 past 9, and when I resetted the timer, it started at 0 hours, 0 minutes, and 30 seconds. So this reset function might be handy for some games if you're keeping track of time, and time plays like a big value in the game. So like it'll be good to create a class time and then just reset the timer at whichever time you need. So just continue on working. And same was for the date. Like I created all the same like in Basiclib time.cpp is the date stamp. It's exactly the same, and like that's how it works. And then I just called the Basiclib date stamp as well to show that it works just by calling the function as well. So there it is, and that's all for the dates and times. So next is gonna be I think it's something to do. The next section is gonna be the strings. So we'll continue from there.
So to continue on with the strings, like I'm not gonna do a PowerPoint presentation this time. It's just gonna go ahead straight to the examples because strings are a bit easy to explain. Still, to create a string, like or define a string is pretty easy. You just go string, like string 1, and then you like whatever you want the string to be, like string equals to a string, so it's gonna be like array of characters. So here like string 1 is equal to string. Then we can create string a bit a different way. Just go string 2 equals, and straight away type in what we want it to be. Or we can take and create string 3 and make it equal to string 2. So this is gonna be like with the uppercase A string because that's what string 2 is equal to. Or we can create another string, pass in a number in there and a character. That's how many characters gonna create inside of the string. Then we can compare strings as well. So if we create a boolean and make that boolean equal to by checking string 1 and string 2, and even though string 1 says a string and string 2 says a string as well, because like the string 1 is lowercase and string 2 is uppercase, they're not going to be equal, so it's returns 0 as a false. Then finding size and positions of the strings. To get a size of a string is pretty easy. So we're gonna make string 1 equals to capital query and lowercase query, and we create an integer that which is named size, and make it equal to 0, and then size is gonna be equal to string 1 dot size. That's just the built-in function, and it's gonna return 12. That size doesn't count from 0; it starts counting from 1. So QWERTY is 6 characters, another QWERTY is 6, so it's gonna be 12 characters. And we can also find the position of the characters in the string. So we define another variable called position, and then that position is going to be equals string that find WE. So when it's going to start to look from the beginning of the string, like when it comes out, when it's going to find the first letter, it's going to stop and return the position. So let's say it's QWE, so we were looking for the first occurrence of WE, so it returns 1, because like it starts to count from 0, so 0 and W is 1, so it returns 1. And if we look for the lowercase WE, it's gonna be 7, because like Y is at position 5, then 6, 7, the first occurrence of lowercase w. Then we can as well say like find w starting from position 6, and it's gonna be 7 again, because like w is at position 7. Then I can show that it works. Like if we pass in value 8, it's going beyond the position of w, so it's going to return -1, which says like it doesn't exist there, because it's beyond the like whatever the string contains. Like there is no w. And we can search for like letters or names or characters, whatever, like in reverse. So if I say we look for the small w again at position 8, like last time, we returned -1, because we type in find, which is reverse find. It's gonna return 7, because it starts at 8, which is E, and it goes back, so it's gonna be 7. Some other ways to find like positions, we can define like another string which is called letters, and type in a bunch of letters in there. And there's a couple of functions we can use, like for example string 1.find first of. So the first letter that it's gonna find in this letters, it's gonna return the position. So when we start looking like QW, so it checks, so there's W, so it's gonna return 1, so 0, 1, so first occurrence occurs at position 1. And find last of, it's like it starts to look for those letters from the end of the string into the reverse, so it's gonna return like position last of 11, because like when it starts at Y, so it goes like WRY up here, and like Y is here, Y is here, so it's 11. I can find first not of, it's just gonna be like find the letter that is not corresponding to the one here, and same with the find last not of, which is just in reverse. And in this video, just last thing to mention is changing cases. So what we can do, like we can define a string, like a random string with like a bunch of capital and lowercase letters, and then in Basiclib we can call a function called uppercase, and we'll make the string that we define here equals to Basiclib uppercase, and pass in the string we want to convert. And that's gonna, like, this is the string we created, and this is converted to uppercase and same to the lowercase. And the way it works, if I can go there, come on, go to okay, I'll just stop the program and explain how it works. So if I go to definition, come on, okay. I'm just gonna pause till I find the function. So this is the uppercase function in the Basiclib string.cpp. So what it does, it takes the string and then it enters into a for loop, which ends when it reaches the size of the string. So by using the square brackets, we access the array of the string, and at each position I, we access the character and convert it to the uppercase letter using the toUpper function. And same idea is for the toLower, and then just returns a string to us. So next is going to be about parsers and a bit more on the strings. So now we're going to talk about how to trim white spaces, extract words from the string you typed in, or remove parts of the string that you typed in as well. So for this example, I'm just going to type in a few white spaces, and then this is a string. So here we can see that it removed all the white spaces before the word this and returned us the string that we typed in, but without the white spaces. So how's it done? In Basiclib string.cpp there is a function called whitespace, and what it does is it accepts a string that you typed in and then stores two integers for whitespace front and whitespace back. Then what it does next, it finds a first occurrence of a character that is not a whitespace, and whitespace is defined as tab, new line, and return in Basiclib string.h. And it does the same by going backwards, so it probably removes the, not probably, just it does remove the white spaces from the end of the string that we typed in. So for here, like for it checks if white space front is actually equals like to 0, like it's supposed like if there's actually no characters or anything, just an empty string, so it's gonna return an empty string. And then what it does, it returns a substring between the numbers of whitespace front and whitespace back, and you have to do minus whitespace front plus 1. So this is going to return us the string between the two numbers that we found. So next thing what we can do is extract the word from the string we just typed in. So it'll ask me which word I want to extract, and let's say I want to extract is, so I type in 2, and it returns me word is. So how is it done? In Basiclib string.cpp there is a function called parseWord that accepts a string and an index of the word that we want to find. So then it has an integer of whitespace start that is equals to the first occurrence of non-white spaces. Again, the white spaces were new line, tab, and return. So once it finds the first character, it's gonna set the number to the whitespace start. Then it enters a while loop, which has a p-index of the word that we want to find. So I'm just gonna read out this comment because it's worded really well. And what it does, it finds the beginning of the next word by finding white space to end the current word, and then non-white space at the start of the next word. So then once the p-index hits to 0, we'll exit the while loop, and since here we found the start of the word, now we have to find the end of it. So we create another integer whitespace end, which will find the first occurrence of the whitespace, and this if checks, like if for example we want to find the word 6 and there's only 4 words in the current string. And so if it's the case, it will set all the white space start and white space end to 0, which will return an empty string because there was nothing you could find. Otherwise, it will return a substring of the white space start. It'll return a substring between white space start and white space end minus white space start. So next thing, the last thing we can do is remove a part of the string. So if we type in, this is a string again, and this time I want to remove a word. So let's say I want to remove is again, so you're going to type in 2. It returns as a string that is a string, so removed is. So how is that achieved? In Basiclib string.cpp there is a function called remove word, so it accepts a string and index. It works exactly the same as parse word up to the stage when it exits the while loop. So it creates an integer white space end and finds the end of the word, and then it finds actually the beginning of the next word as well. Then it checks if we could actually remove anything or not that we specified, otherwise it's going to just return or erase nothing. And then what it does, it creates a string that is equal to the string we want to erase the word from. And what it does, it actually calls a strings function called erase, and it erases the word from between white space start and white space end minus white space start, and it returns the string to us. So next thing we're going to talk about is string conversions. So let's say we have string 1 and string 2, and string 1 is equal to 25 and string 2 is equal to 26. As we know, if we add two strings together, we're just going to end up with not a mathematical calculation, but they're just going to be added as two strings. So string 25 plus string 2 26 is going to be 2526, not 51. So let's say we want to convert those strings into integers. So up here we create int a that is equals to, we call function from the Basiclib called toType, and in angle brackets we specify what we want them to be, what kind of type, and pass in string 1, and same for int b, we pass in string 2. And again, when we add them, up here, we're going to end up with 51 because now they're integers. So how is it done? In the Basiclib string.h there is a function called toType, which is a template. So in the toType, in those angle brackets, we have to specify what type is it, and then in here we pass in the string we want to convert to whatever, float or integer. And we create a string stream that takes in the string we typed in. There we create a variable of type t, that is t, and extract is basically taking the string stream and whatever was in that string stream we put it into t, and then we just return the t, which is going to be int if we specify it in the angle brackets integer, and that type will become the integer. And that's how we end up with the integer. And now let's see how we go about to convert integer a and b back to strings. So we're gonna do a cout that says a and b converted to strings and added. So in that cout, we, instead of creating new strings, we're gonna just convert it straight away inside the cout. So we call from Basiclib we call the function called toString. Then in this toString we want to specify from what type we're gonna convert the variable to string. So in angle brackets we say int, and I pass an a, which is an integer, and then I add same toString of b, like because they're back again converted to strings, they're not going to end up as 51, they're going to end up as 2526 because they're back being strings. And in toString function again, like if you add a number after like the variable a here, like this number will add like 10 spaces with for that converted integer. So that's what we see here, like when it prints out it has 25, and then like this is going to be 10 spaces and then 26. So in Basiclib string.h there's a function called toString, which again is a template. So what it does, like inside angle brackets you're gonna have to say from what type you want to convert it to string. Then I don't know why it says p type here. I would expect it to be just like the string we want to convert to, and this p width is just like the spaces we want to add, but by default it sets to 0. So again we create the string stream, and then we insert into the string stream like whatever we want to convert. Then if string is larger than width, just return the whole thing, and otherwise like we add as many spaces as needed after the string if not. So we return the string plus the amount of white spaces we want to add to the string. So that's how we convert to the string, like integers, floats, or whatever we want again. Now let's see how we go about to search and replace something in a string. So we have here like a string 1 that is equals to 1, 2, 3, 4, 3, 5, and let's say we want to replace 3 with something else. So we're gonna take the string 1 and make it equal to Basiclib and call the function search and replace. So with search and replace it takes in the target, which is the string, and then the second one is like what we are looking for, and the third variable is like what we want to replace it with. So we want to replace 3 with 0, and that's what we're gonna end up with here, like 120405. Then let's say we want to replace 0 with that smiley face. As you can see, nothing happens because this 0 is lowercase, and like nothing's gonna happen because like you have to be careful like which like if you enter stuff with uppercase or lowercase, it's gonna search for exactly what you wanted to find. So maybe to avoid that, you'll want to put everything into lowercase by calling basically lowercase function and just convert that string 1 into lowercase, and then search for 0 and replace it with smiley face. So that's what we're gonna end up with, 1, 2 smiley face, 4 smiley face, 5. So that search and replace function is found in the search and replace. It's found in basiclib.string.cpp. Excuse me. And so, like I said, it takes the target, what we're searching for, and what we want to replace it with. So we create a string that is equals to the target. Then what we do, we have this size type integer, I presume, like yeah, it's size type I, and that I is gonna tell us how many times the what we're searching for occurred in the string we're looking at. So then it's gonna enter the while loop and replace that what we're searching with the p replace that we want to replace it with, and then just like when I is gonna be equal to the string's length, and it's gonna just exit the while loop and return the string to us. So yeah, that's how it's done. So the last thing to cover is the logger. So to create the logger, what we do is we call basiclib and then call the text log, and give a name to that text log variable. In this case it's going to be system log, and inside the system log we have to specify the name of the file we want to write the stuff in. So it's going to be system.txt, and the header of the system.txt file, like inside of it, is going to be written like this is a system log. So like this is the folder where the Basiclib is. So when we run the program, and we can see it creates a system log. So there's the header that we gave to it, like system log, and it says like when the session was opened. So if we're gonna keep just writing random stuff into the file, so it doesn't matter what it is, and then we quit the program. So if you open the text file now, we can see everything that we wrote down, it was appended to the file, and then when we exited it successfully, it's gonna create a session closed. Then like how do you append actually to the text file? Like you call the system log and then go .log, and whatever we type in into this brackets is going to be appended to the text file. Now to look inside of the code, the code is in Basiclib logger.h. So there is a class text decorator that's just for everything that does this kind of stuff, like decorates the text file itself. And the session open just returns a new line, session close returns a new line. Then the logger itself is a template. So and then the logger takes in a file name, the log title, and it has all the timestamp set and date stamp set to false by default, and it has a destructor as well that creates this session closed when we successfully exit the program. If you're just gonna press like X, it's not gonna do that. So when we actually create the logger, so the first thing it checks the first thing it checks that if the file actually exists. In C++ there is no easy way to do it, so what they do is like they create the dummy file tester and then try to open that file in only readme mode. So if it does exist, they close the file tester and open the actual file in the appending mode, so whatever we write is not overwritten, it's just gonna keep appending to the file. Like if the file doesn't exist, what it does, it creates the file and creates the header as well, because since it's a new file, because we don't want to create the header every time like we enter our program. So then the timestamps and date stamps are set to true, and so we could keep track when the sessions are opened and closed. Then in destructor, like I said before, like when we successfully close the program, destructor is called automatically and it creates the session closed with the timestamp and date stamps. And the log function itself, like, is whatever we type in here is gonna be like appended to the text file, and that's pretty much it. Well, like this decorate, you could probably like mess around with this as well and add your own decorations if you need, but it looks fine the way it is. Like, so there it is. Thank you.